Take my book notes.
No, I have many. I have
Three pages, because it's a long.
yeah. Well, if you need more, just that. So.
If you run out, let me know and I'll stop.
No, there is this. The nicest thing of Toronto is Dollarama, if you ask me. Dollarama, so you can get so many pieces of paper for like $1.
Did you find the time of with Gerson?
Yes, I actually forwarded the email. So which one are you using?
No, just Wednesday it's 4 o'clock, but Friday it's 3 o'clock, huh?
Exactly.
No, Friday it's
And nothing on Thursday, nothing for Thursday?
Thursday.
Or is there?
Yeah, Thursday there is one.
It's at 3 o'clock.
Oh, okay, so I need to do something about my schedule. Because I have a class at 3, but I can, yeah, but I can rearrange. Yeah. We'll see, or maybe for the other people too, right? Okay, maybe we make a change there. Okay.
It's okay. Meeting.
I think we're all okay. Okay, let's go. All right. So today I'm continuing. There was a little, we've kind of shifted gears and we're talking about systems now, but I started by, as we did at the beginning of the scalars, I started by talking about the inviscid case, the hyperbolic case, just as a background. So we're continuing that for the first part of the lecture, and then we'll start in the viscous stability issues in the second part. But we're going to make reference to what we do in the first part here very much, so it's useful. All right, and I did want to mention, so last time we showed that fixing an energy as a function of volume and entropy leads to compressible oil. And fixing S identically equal constant gives isentropic compressible oiler. So that was 2 examples of, and both had, and this had an entropy. It's built in. This is the entropy. So it's an example of the things we talked about. But I forgot to mention, for isentropic compressible Navier-Stokes, it also has a mathematical entropy. We got rid of the thermodynamical entropy because we set it to be constant, and also that makes it non-physical by doing that. But the equations, they still have an entropy, but it's it's convex. And the entropy would be yeah, I'll call it Q of rho, Q of rho plus what is the rest of the entropy? Plus rho U squared. So it's a kinetic and potential. And here, Q prime of rho is equal to P prime of rho over rho. Turns out. And so for this to be convex, we need this to have a sign. That only requires that the first derivative of pressure have a sign. So it's convex if P prime is positive. And that's a very minimal assumption. We need that for hyperbolicity. Whoops. Just hyperbolicity implies that this is necessary for hyperbolicity. So almost every time you get a good convex entropy, And that's independent. This equation we could just write down. We could forget about the derivation from an entropy formulation, and we still have a good mathematical entropy. Okay, so we really do have two example systems to keep in mind if we like. Okay, so that's old business, and now the new business. Okay, so the Lopatinsky condition. I'm going to introduce, and this is for Hadamard type or well-posedness stability of an envisaged shock, Okay, but you may think we already did this. Was it not the lax characteristic condition? Oh, it's not quite. Okay, but let's recall. The idea is you have a shock curve, x of t. You have incoming and outgoing characteristics. This. And what do we need to determine? So, well, if we linearize around a constant state, it's completely diagonalizes. So the flow on the left is just propagation along characteristics. And on the right, also, the characteristics that enter the shock, they're unimportant. They just carry information to the shock. What we need is a boundary condition that is telling us what leaves the shock. Okay, so we need to solve for outgoing characteristics plus the shock speed, because that is a free it's a free boundary between the two waves. And we only have one piece of information, and that is conservation in the form of the Rankine-Hugoniot condition. So we have a jump condition. And the jump condition, if you recall, it was x dot of t, jump in W equals jump in F. And here it's dt W plus dx, F of W equals 0. And this is the Rankine-Hugoniot. So it's n conditions where n is the dimension of the variable. So we have n conditions. So we must have n minus 1 outgoing waves or outgoing characteristics. Because we have to, using these n conditions, we have to solve for all the outgoing waves and the speed. So we can only accommodate n minus 1. That's the lax characteristic condition. But of course, we know that's never quite enough. That's just a consistency condition. This is a linear system that we need to solve. So there's some kind of determinant condition involved in here for being able to solve this. So we have to think a little bit more about this. So what we do is we want to linearize the Rankine-Hugoniot condition. And then we use an implicit function theorem argument to say, if this is full rank, then we can, for nearby nonlinear perturbation, we can solve. So we need this to be full rank. And this is the Lopatinsky condition, which that arises in many different settings, not only here. And okay, so let's linearize. Let's start again. I'll rewrite RH, which was okay. I'm going to call it S for speed. Jump in W equals jump in F of W. If we linearize this, then it becomes S, and I'll use W dot and S dot as perturbations.
Linearize near what?
Linearize near a near a base point, base points WS, satisfying RH. So we start at some given fixed shock, and we're going to ask, well, as we vary the parameters, can we still solve this boundary value problem near that fixed shock? So I'm going to introduce, I like this notation, I'll put dots to be the perturbation variables. And so this becomes S dot plus, SW dot plus S dot W, jump in W, equals, okay, and this becomes dF over dW at W, W dot.
But this dot is not dot, right? This is DDT, the X.
Oh, yes, I'm sorry about that. Yeah, so let me write it like that. Let me write a prime. That's confusing. Yeah. Yeah, now I want to use it for perturbation variables. Okay. And so, okay, so this is, okay. So this is what we've been writing as A. And it will be, right, I typically used A of W equals DF over DW of W. This is the notation we've been using all along. So I'll just put A here, but it needs a plus or a minus because it depends if we're on the right or the left, because there are two end states. So I should have said W minus W plus this. There are lots of variables. And okay, so then I can move this to the other side. And I have, okay, S dot jump in W equals A minus S W dot jump. So this is, the jump means the difference between the plus, which is the right-hand side, and the minus. So this is A plus minus S W plus dot minus A minus S W minus dot. So these are the changes in waves on, right? They break apart into incoming and outgoing modes, and they will have some portions. I'll write these as summation of Wj plus Rj. J equals 1 to n, and these likewise. Summation J equals 1 to n, Wj minus J minus, where these are just the coordinates in the different characteristic directions. These are the characteristic directions, the eigenvectors. These are the eigenvectors of A plus or minus. And I'm just expanding in eigenvectors. And these get a dot, right? And some of them are outgoing and some of them are incoming. And I need to be able to solve this. Okay, so here, this is a fixed. This is WS dot W plus minus W minus. That's just a constant, a coefficient in this equation. And A plus minus S, A minus minus S, those are all coefficients in this linear system. And the unknowns are just the W dots and just the dot variables and the S dots. Okay, but remember, we consider okay, so AJ minus positive are incoming, and AJ plus negative are incoming to the shock. These are characteristic speeds that move greater than S, less than S, right? And those are fine. Those are these are data. What we want to solve for is the outgoing ones. we want S dot and Wj plus dot such that Aj plus is less than, sorry, it's greater than zero, greater than S, and Wj dot minus such that Aj minus is less than S. Unique solution. And well conditioned. And for that, okay, there's a certain determinant condition. But I don't ever have to write down what that system is because I know that for a linear system, it's the same to ask whether there's a unique solution of the homogeneous system. So it's equivalent to take all the outgoing modes to be zero, just to take them to be zero and to say that there is then no non-trivial solution. Now, so now I can formulate the condition. So what am I trying to do? I'm trying to express, let's see. I'm trying to say there are no non-zero solutions of this equation involving only the outgoing modes. Okay, so that is just trying to ask whether these are linearly independent or not. So the question is jump in W, which is W plus minus W minus, this is a vector, and Wj plus outgoing and Wj minus in outgoing. This set a linearly independent set. If it is linearly independent, then viewing S dot and oh, sorry, these are not W's but R's. It's the R's that I want. Those are the vectors. Those are the directions. Because the dotted variables, those are just coordinates. Those are just numbers. Those are the coefficients of these different vectors, and I'm asking whether there's a non-trivial linear combination of these that's equal to zero. And so I'm asking, can zero be equal to the determinant of jump in W? And then we have A plus minus S Rj plus out, A minus S times Rj minus out. But notice it can be even simplified because these are eigenvectors of A. So this is equal to the product of Aj plus minus S over outgoing times the product of Aj minus S outgoing times determinant of jump in W, Rj plus out, Rj minus out. So all the outgoing eigenvector modes, or outgoing eigenvectors, or outgoing characteristic modes, I put them as columns in this matrix, and then I put the jump in the shock jump as the first column. And the question is, and these are all non-zero by Lax, because of the Lax characteristic condition, that's a basic compatibility condition. It must hold. And then this is the fine print In fact, we need more than that, right, to make it a nice, well-conditioned system and apply the implicit function theorem. We need full rank, and this is the full rank condition. That's all it is. And it's not too bad, right, in the end.
Okay, plus it means the.
All of
the
them,
list.
yeah, the list. Yeah, I should have written it as a set, right? It's a set, the whole list of them.
N of them.
Yeah, there will be in total n minus one of them. That's the lax condition, and then this completes the n columns. So okay, and yeah, so usually we just ignore this factor, and this is the
It's not, it's
is what known the
the factor.
Oh, I mean, we could write it out. We could write it out because we know, in principle, we know these. We can compute these eigenvalues that are going out or in. Otherwise, we don't even know the lax characteristic condition. So presumably, we've computed these. The sign, and they're all different from the shock speed s, right? Because they all have to enter or leave. That's part of the lax condition. There should be no, characteristics. No characteristics that are characteristic with the shock. That's not allowed. So each of these will be plus or minus, and we can count how many are plus and how many are minus. But that depends on the particular shock. And so this is so non-vanishing of this, or I sometimes call this delta. Or I don't know why I like that as a. I do know why, but yeah. It's connected with the Evans function that I called D at some point, capital D, and then there was a delta for something, and then this was a big delta, and then there was a little delta. So a complete accident. Yeah, I do know why, but it's not worth, it doesn't mean anything. Okay, so maybe I'll just mention a couple of things. And okay, so for compressible Euler, we have one shocks and three shocks. These are the acoustic modes sometimes. So remember, there was an entropy that is just conserved. That's clearly one of the modes. But it's not very interesting. It's just convected with fluid speed, and it does not support shocks. It supports another type of simple wave called contact discontinuity, which we're not discussing here. The one shock has, okay, characteristic A1. I'm going to order them. I'm going to take A1 less than A2 less than A3. Okay, and then here's speed S. Okay, so this is the one family. It will be compressive. It will look like a scalar shock in the one family. This is A1 minus. Oops, there are three. And then we have A1 plus, A2 plus, A3 plus. And if we look mode by mode, this is what the one family looks like. Here's the two family. And here's the three family. They're just, the two and three, they just pass through the shock. Okay, I should have drawn it a little better, like this maybe, different speeds. But they just pass through. And this one looks like a scalar shock in the one characteristic direction. That's the idea. So when you hear people talk about a one shock or a three shock, so this is a one. A three shock would be the reverse scenario where everything is entering on the right. And then only the three mode is entering on the left. This is a lax three shock. And now it looks like this this. Actually, the middle one doesn't change. And then the third one looks like a scalar shock in the three characteristic family. So it's kind of in one family, it's compressive, and in the others, it's just moving through transversely. Okay. And these the ones these have the property that they're extreme shocks, so-called, because they're either the smallest or the largest characteristic family, and it simplifies the writing. So for a one shock, delta is determinant of the jump in the end states, and then okay, so let's see, and all the outgoing waves, it's just a R2 plus R3 plus. So I don't have to write my list, my abstract list. I know what they are. They're just all of them but the one on the right. And for a three shock, then delta would be determinant of, again, the jump in W, but now it would be all the outgoing modes for the three shock, which would be A1 minus and A2 minus, sorry, R1 minus and R2 minus.
Excuse me, can you explain the pictures for the three shocks?
Oh, these here? Okay, so this is this is for A1, this is for A2, and this is for A3. I'm just looking at the three characteristic speeds. And here is A1, A2, and A3. So I'm just taking, okay, so this picture is a picture of the propagation of characteristics on either side of the shock, and I put them all together. I think this one makes sense. It's this one that you're wondering about. Yeah, so I just took them separately. If here I'm looking at all three characteristics, here I'm taking them one at a time. So this is A1 minus, A1 plus, A2 minus, A2 plus. I should have put more, I think.
The picture on the left.
Yeah, and it corresponds to the picture on the left, and we see that every time there's only one that's going to be compressive, and all the others have to have the same sign on both sides. That's because there are n-1 outgoing waves. It's a sort of pigeonhole principle. There has to be precisely one that is compressive in this setup. And that family is called, the shock is said to be of that family. And this is why, because if we think of things as being decoupled, which they aren't really for large shocks necessarily. A lot can happen between 0 minus and 0 plus if you have a large discontinuity in terms of the wave structure. So
and then why for the three shocks the determinant reduces to
okay, so yeah, so for the one shock is this one, and the three shock is this one. So I'm just saying that in these simple cases, the bookkeeping becomes easy because it's only outgoing on the right-hand side. For the one shock, the only outgoing characteristics are the ones on the right-hand side, and they're the ones that are the larger. So their eigenvectors are just R2 plus and R3 plus. So I can list them in a convenient manner. Okay. Likewise here, if I have a P shock with W in Rn, then delta is determinant of, see if I can get it right on the first time. Okay. So I will have R1 minus up to Rp minus 1 minus, and then Rp plus 1 plus up to Rn plus. If I got this all right, there should be n minus 1 of these. And I think they are. So it's precisely the P family that is incoming and doesn't, yeah. So you just exclude the family that of your shock, and then the other eigenvectors have to all be represented there. So it's not so terrible bookkeeping. Yeah.
In the three shock, essentially the plus don't exist.
Yeah, right. Yeah, that's true. But also now it's worth for what I'm going to tell next. It has very much to do with extreme shocks. And I want to make a comment that if all the waves are incoming on the left side really has nothing to say about stability. You could put some perturbation here. It just propagates according to the Cauchy problem with no boundary. It comes into the boundary as data, it's gone. And there will eventually, after a certain time, there will be nothing here. So it's sufficient to treat the case of zero data on the left and only treat stability on the right. I think that's what you're saying. Maybe. Anyway, if you're saying it, that was a good comment and anticipating where we're going here. Okay, so yeah, so things become, a little more complicated all of a sudden. It's not just counting characteristics. You have to do some computation. Right. Okay, and one comment before I discuss this. This relates very much to Riemann solutions. So recall the Lax theorem and the wave map formulation of solving a small data Riemann problem by a succession of shock and rarefaction waves that are small. Okay. Well, here we're looking at near a single shock. This is for small data. Single large shock. And we're asking, okay, so, but the Lax theorem tells us small perturbations can be represented as a succession of small rarefactions and small shocks in the other families. So we have families, large P shock, P being the family, and then we will have families A1 minus through AP minus 1 minus on the left, AP plus 1 plus up to AN plus on the right. Okay, so we start with a single strong shock. Moving up, okay. This is the solution of a particular Riemann problem, the one with the base points W minus, W plus, and speed S. And now we're asking, well, what if we change the two end states a little bit? Is there still a unique Riemann solution? Well, it's actually the same question, because we can represent small perturbations as a succession of small rarefactions and shocks on the left and small rarefactions and shocks on the right. And the question is, can those be accommodated by a change in the shock? Is there another nearby large shock that accommodates those? It's the same question we just solved. This is equivalent to the full rank is equivalent to delta not equal to 0. So there's some connection between uniqueness of Riemann solutions and stability of shocks. It comes through this Lopatinsky condition. But also, these Riemann solutions are really interesting. They're scale invariant, so they're large time behavior, and they're also capturing small time behavior. And the original proof of existence by Glim used the small behavior in the small. So somehow uniqueness and existence are all and stability are all tied together loosely. And so we should be alert to connections.
So once you have this determinant non-zero, you can solve the S dot and all the dots.
Yeah, and the dots on the left and the right, which now are very small waves in the other families, small shocks or rarefactions that build into the wave map. And maybe it's nice to, let me try a 2D W1 and W2. So we're starting with just a single shock here. Okay, if it's just W1 and W2, let's make it a one shock. So all that I'm allowed is I can go from this end along the 2 Hugonio curve. So the question is, can I get from W minus to some, or from some nearby W minus to some nearby W plus by a shock in the 1 family, oops, plus a small wave in the 2 family, either shock or rarefaction. It doesn't matter. They're both parallel to R2. And the answer is yes, I can, by the implicit function theorem, if this full rank condition holds. And that's pretty interesting and important to notice, because it's not really clear what does this kind of instability signify. We would, this always bothered me. Imagine you start with a small amplitude shock. By the way, I should have mentioned, this is always satisfied in the small amplitude limit. Why? Because the jump between left and right states of a P shock it's basically parallel to the Hugonio curve, the P Hugonio curve, which is RJ. That would be in the small shock limit. This would be approximately RP. And by the way, plus and minus would not make much difference. It's small amplitude. They would all be, I could drop the pluses and minuses. Well, that's the missing, this would be RP. That's the missing way. That's the one missing eigendirection. And so if you allow me to drop the pluses and minuses, because they're all close together, and you allow me to substitute RP here, I'm just saying that I have a full set of eigenvectors. But that was built in by hyperbolicity. I've assumed that I have real and simple eigenvalues. So I have a full set of eigenvectors. So this would always be non-zero. The real question is for large shocks. So the thought experiment I'm always thinking of is, okay, let's make the amplitude of the shock larger and larger. Let's move farther and farther along the Hugonio curve. It starts out stable. After a while, well, maybe it becomes unstable. Okay, but then according to this, shortly afterwards, it becomes stable again. That's really weird. That doesn't make sense to me. But if you keep this in mind, it's not weird at all. Let's see. I guess I want to. It's not weird at all. But what it's telling you is something interesting. Is that we're basically fixing W minus, and we're moving along this curve. Let's call it W of theta equals W plus. And theta starts at 0 and increases. So I'm just going to keep moving along. These are all solutions to the Rankine-Hugonio curve. And so there's an associated speed for each theta. And there's, so at least in the small, that's true. That's part of the Lax theorem. Right? It says that you have such a curve. And it's going to continue so long as the full rank condition holds. And then there's going to be some special theta star where delta equals 0. And what does that mean? Well, what it means is what's called shock splitting in the literature. And I think it's Claude Gardner, the 50s, mentions this in a really interesting paper, and many people have mentioned it. Also, there's a really nice paper by Menikoff and Flor much later discussing this and this, and they mention this shock splitting. By shock splitting, I mean there are two solutions. Afterward, this is a bifurcation point. It's a bifurcation in the Riemann solution. So one solution is just like this. So here's my theta star, W of theta star. Here's my W minus. So at this particular point, now something happens. Okay, but I still have the Rankine-Hugoniot curve still continues, typically still continues past this point. So I have shocks to deal with, but what happened here? Well, what happened is, it turns out there is another wave, a shock from, let's see, how would this go? A shock that, let's see, W1 to W1, I can get from another shock. So to here, well, it's becoming parallel. This is hard to draw, but there's another shock. It's in 2 by 2. It's harder to draw, but let's think in three space. So there's some other shock that gets connected by the two other families to the same point. That happens later. Here it's just kind of a tangency, but later it splits up. Typically, if you look at the Rankine-Hugoniot as describing a solution set, it's describing some manifold in the space W minus W plus S. There's a fold. And now there are two solutions. Okay, so there are two different Riemann solutions. Well, which one is going to be picked? And numerically, only one is picked. Not the other. So here, this one is picked. And it's selected. Afterwards, it will not be selected. The one, if you just continue along the Hugoniot curve, you'll get a shock in the abstract, and it satisfies the Lax condition, seems okay. But if you run the numerics, that's not what comes out in the behavior. What comes out is the other solution. So it's apparent exchange of stability. As we expect, right? We often, in bifurcations, we typically expect that when our solution becomes unstable, we expect the other one to become the bifurcating solution. We expect a bifurcation, we expect the other one to become stable as we lose stability. But here it's more subtle because it's not clear that we lost stability. We don't really see it. We see that something happened here that's not so good. Okay, and so this problem was posed to me by Bert Windruff. I had my first summer internship my first job after I graduated was at Los Alamos, a summer internship. And Bert Windruff said, "This is a great problem. Why don't you figure out why is it becoming unstable?" And so I read a lot, but I didn't get anywhere. But actually, in the end, as I noticed as we had developed more and more progress, hey, wait a minute, I know the answer to this now. So we can answer this. I'll answer this later. But basically, I mean, and he already said this, probably this is numerical diffusion from the scheme. And what it means is that the viscous stability is changing. And that's exactly true. But to then be able to say that there is an exchange of stability by looking at the viscous shock, that's pretty interesting to me. So that's a really interesting 1D problem to me. And it was yeah, great. That was a great direction. I wasn't ready. That was 15 years too early. But it's still a great problem. Menikoff and Plohr, P-L-O-H-R. He did a lot of fundamental work on the the structure of Riemann solutions, on some of these things related to the equation of state, and then the structure of Hugonio curves and things. At a certain point, he and Menikoff and Dan Marchson to some extent. This is not Robert Gardner. No, it's not. This is a previous Gardner. He did some work on stability of plasma shocks, and yeah, he was an earlier worker in the 50s and did some. I really like his papers. He has some nice results and a nice perspective on things. And right, and I'm going to mention more about what he said, more than one thing in this paper. Then he mentioned the shock splitting, but there's more. But first, let's see. Yeah, I'll mention that and a couple other things. And okay, so Midas theorem 1D is that the Lopatinsky holds for all shocks in ideal gas. In the ideal gas with the full compressible Euler, also isentropic. And that's a nice calculation. That's pretty easy to do. This is P of rho. P of rho equals constant times rho to the gamma is an ideal gas for isentropic. Okay, both these cases perfectly good. And the Hugonio curve extends on; it never stops. You can solve any. And the remark is that the Riemann problem is uniquely solvable for all values. That's globally. So that's very satisfying, even surprising, right? Because these are all approximations. And especially the choice of viscosity coefficients being constant, that's an approximation. You don't really know what they are. They should change with temperature, kind of lot, intuitively. All right. Anyway.
For all time?
Globally in W. So for every left and right state, we can find, at least with temperature positive and density positive, so physically acceptable states. Take any two, there's a unique way of connecting them with simple wave solutions, which we expect to be the large time behavior if we put data with those limiting end states. We expect to segregate into non-interacting waves, so they do it very nicely. Okay, it holds for all, but okay, so Gardner, same one. He says that there exists a nice convex equation of state, E of VS, and all standard properties of small amplitude ideal gas, but unstable. And yeah, he says, he mentions the shock splitting, which I don't think had been really, I don't think that connection had been made until he made it, or not. I don't find it in the literature. So that was a very, very nice comment. But he says there's no reason why they should all be stable just from considerations of, well, things like entropy decreasing as you move along the shock, genuine nonlinearity, well, many standard things that people assumed. And he said you could assume all these and still have an unstable shock. And he gave an example, but the example wasn't quite right. But everything he said was right.
We're talking about one.
This is still 1D. This is all 1D. Right. In multi-D, these kind of, all bets are off. The Riemann problem would be, you have to decide what you think it should be. Should it be? Yeah, he said he invented an equation of state, and it had a convex entropy. So people were trying to move past ideal gas to real gases, and say, well, what can we salvage from the theory, or what would have to be true of a real gas so that we can still analyze it in the same way? And when does it become kind of crazy, like a van der Waals? It was known that there were gases that don't behave in this nice way. They have multiple phases and things. But so especially some names, Hans Bethe was one that did a lot of work on this. Wow, Bethe. Who else? Well, I guess Gilbert, to some extent, was involved in the shock profile problem, similar issues, and then Gardner. And okay, and then so this is too technical, but I'm going to refer you to Barker. This is a paper of mine. Barker, Freistuhler. And it says something about convex entropies and dot, dot, dot. And in this, we fix Gardner's example. We find an equation of state that looks really pretty almost the same as his, but now it works. But in between those two things, there's a huge body of work. And this is built on Randall Smith. So I guess he's my, this is a student of Smaller. A little smaller. So he's my academic uncle, I suppose. And he wrote a fantastic paper in which he completely characterizes uniqueness of the Riemann problems, or Riemann solutions. Like for which equations of state do you always have globally have a unique Riemann solution? For which do you not globally? But sometimes, and if you think about it, that is a real tour de force, because it's not a local condition. You've got the Lopatinsky. First of all, you have to find, where does the shock curve go, the Hugonio curve? What are the states we're thinking about? And then we have a condition that has to hold on all of these curves. It took tremendous geometric insight and force and perseverance to do this. And this was for not just a single large shock, but now could be many large shocks together. So that's more difficult. What we were after was just stability of a single shock. That's a weaker condition than this. And then you have to understand what Smith did and do the weaker thing. And so it was actually very, very interesting. And I think if you found these kind of thermodynamic considerations and equations of state, if you found that intriguing, I would look in this paper. Even though, it comes in, the ideas are almost all here, but I feel like we revisited them and made them clearer. Anyway, it's clearer to us. I can read this, and I can barely read that. But to an outsider, it might be the same. But yeah. This is 2000, and I think it's 2015. It's not that long ago, but not that recent. This one was 80s. In the 80s, yeah. Oh, yeah. And then and it seems that he left this area completely. And I can understand. That was a big job. Okay, so that's where we stop here, and I'm going to come back and show you a real gem. It's due to Alexis Vasseur and his co-author Leger. They found a condition that it sounds a lot like these nice conditions that they were trying to impose, that Gardner says, no, those aren't enough. And we show, no, those aren't enough. And he has a condition that is enough. And it's amazing. And you might see it and think, well, oh, okay, of course you would try that. But this is after many, many failed attempts and counterexamples, decades of it, and then this pops up. So I want to show you that one. It's pretty neat. So let's take a break and then come back.
First name
Ah,
Too many of them.
I think
it's okay.
I'm not sure. I thought it was H. I thought it was a server mile, but I'm not sure. I'm not sure. Yeah. Yeah, it's quite yeah. And then a really interesting unfolding story. And then what I found is if you go back to the earliest, and then of course, it kind of starts with Riemann, right? With his investigations, and it's extending from there. If you go, the further you go back, then sometimes the more modern it sounds, because they were thinking of all possibilities. And then for a while, people focused on what they could solve, and you go on along a track, and then you say, well, let's try, now we're feeling ambitious, let's try something new. And the first guys, they were mentioning all those things that you're now trying, because anything's possible when you first enter the field. Okay, so let's stop for a minute, and we'll come back in about 3:08 or so. Okay, we still have picture and everything out online. It looks good. Ah, okay. Okay, so we're going to go back to, so this is the condition of Leger-Vasseur. It's a sufficient condition for stability. And all these kind of things I mentioned were intended to be just sufficient conditions. Like if we know some certain nice properties, then it should be good. And it has that flavor. Okay, so let's go back and remember which what? Yeah, this is recent. Okay, so yeah, this is in around 2015 as well. And it's actually it was the opening shot in just a barrage of results by Vasseur and his group using these ideas of relative entropy that I'm going to show you, and contraction, and it's gone very far. And so they did a lot of things with this. This was like the very first thing, and it's already really really surprised me. Okay, so entropy flux pair. That's just to remind you. We talked about this first day of the course, I think. That's an eta and q, and of course here's our equation. So it's eta of q such that d eta df equals dq. And we want eta convex because that gives us, that gives us dt eta plus dqx less than or equal to 0. So for smooth solutions, this would be 0 by calculus, by this fact. The point is that at shocks, the entropy is not conserved The only entropys that are conserved typically are linear functions of you know, a change of linear change of coordinate. Linear functionals basically. If the eta is constant, this always works. Okay. All right. And this gives dxq. Yeah. And that implies that if I take integral of eta of x dx, d by dt, that's minus dxq, that's equal to negative integral dx q. And if I take q plus or minus, if I take w, limit at infinity, w of x equals constant, then this perfect derivative will vanish, or this is less than or equal to 0. So it says there's a decreasing functional. And if eta is convex, I can always choose d eta over dw at w naught equals 0 by adding a linear part. I can always renormalize it a bit. And this would be a convex, it's equivalent to the L2 norm. So if you have an entropy, it gives you control on the L2 norm and stability of constant solutions. So if I take it, this constant solution, any constant is a solution. So take this W naught, and I'll perturb it by something in L2. This says it never grows, the L2 norm, well, it may grow by a constant factor, but eta, which is equivalent to the L2 norm, will in fact decrease. There will be a contraction. So this gives a contractive L2 type norm. But around shocks, there's two states, right? Two states. So it's not really controlling the L2 norm. I could normalize it on one state, make it good. I could normalize it around another state and make it good. But anyway, so let's define a relative entropy. Eta of u, of w naught is going to be eta of w minus eta of w naught minus d eta at w naught, which is, that's by shorthand for just the differential, times w minus w naught. So this is adapted. So for w naught constant, this is the L2 equivalent contractive norm. That's exactly what we would do to it to make it useful for proving stability of the constant solution, W identically equal to W naught, just as I described above. But, and this, I believe this starts with ideas of de Fermos, and I'm sorry, I don't know the date of that one, but de Perna around, I think, let's see, I wrote down 1979. And I remember also, in this case, I remember where it appeared, Indiana University Math Journal. So they had the idea, okay, what we need to do is not just take relative entropy around a constant solution, but around, let W not be another solution, and see what we can do with that. And it turns out you can do pretty much with that. as long as the other solution is Lipschitz, then this is useful. So this Duperner paper is basically proving the most well-known part is if you have a Lipschitz solution, it's going to be unique, and you use this relative entropy to show that. It's like a weak strong kind of thing. It's unique even among weak solutions, and this relative entropy allows you to prove that. It's basically just I've taken a random convex function. Here's W naught, and I've transformed it to one that's convex and flat at W naught, and that's what I want. All right. And all right. So here is the idea of the result of Leger and Vasseur, as I understand it, and I got on my trip back home over the spring break, I got a tutoring on this from Vasseur. So hopefully so let me properly present what you were thinking. Okay, so the idea is this is going to be for an extreme shock. So without loss of generality, a one shock. And so thanks to the question of Catherine, we already have an important part of this, which is that so every characteristic is entering this one shock from the left, and one is entering from the right, and n minus one outgoing. But okay, but a big important, and then we have W plus over here. That's the other side we're imagining, and these are small. These are well, possibly big perturbations. One of the great things about these entropy, there's no discussion of smallness in there. It's a global construction. So first of all, we can just set this to be 0. Because whatever's there, it gets carried through the shock, and we'll deal with it on the other side. But so we'll just take that from the beginning to be 0. All right, but still W minus persists. The left end state is still there. We have to connect this shock always to W minus. So there's a state. But the problem is a little bit simpler now, a little more manageable. Notice it does apply to gas dynamics. This is the only shocks are extreme shocks. So that's fine. It will be sufficient to deal with to recover Midas theorem and many others. Okay, and all right. So this is the idea. So we want contraction. By which I mean that the integral from xt up to plus infinity of eta of u, okay, I'm going to call this, sorry, not anymore, WR. Of x. I want this to decrease as t increases.
WR is defined.
WR, so where the shock is from W minus to WR. And speed, what do I use below? I think I used sigma. So it's just the right value here. Okay, now here is the funny thing. So they assume existence. And a sufficient measurable properties that we have just a one shock for almost all time. And if you think of that, that makes sense. If you have, it's not going to always be the case, because basically you're sending in little waves, which could be shocks, by the way, whatever. You're sending in waves. It's basically a Riemann problem all the time. And we know that Riemann problems can emit shocks. So coming out, but they only, but the time at which there's, let's look at a Riemann solution. It initially has a shock, but it initially has a pair of shocks, but they immediately separate. So you don't have for most of the time, you don't have a pair of shocks. You just have one shock. And so that allows you to ignore these other times. And you basically assume that you can assume that you have a one shock at all times in this calculation. Okay, so that's some of the hard part. I'm just going to sweep it out. This is just for, by the way, this is only for intuition for us, because we're going to prove that their condition that they derive from this point of view actually implies the Lopatinsky condition. Okay, so here is what you want is, all right. Their theorem is, so let's define S of theta equals the Hugonio curve. S of 0 equals W minus, and S of theta, and W minus S of theta, sigma of theta satisfies the Rankine-Hugonio condition. With the Rankine-Hugonio full rank everywhere. So that means the linearized problem that we solved is full rank. That's not the same as, we'll see it in a minute. It's not the same as the Lopatinsky condition. It's simpler. Just Rankine-Hugonio only involves really it involves less. Just the shock, not perturbations. And 1. D sigma over d theta is less than 0. 2. Eta of W L W of theta minus eta of W L W R is bigger than or equal to 0. Then it's contractive. So stable. In another sense of the word stable, not Hadamard stability, L2 stability. So Hadamard stability is partly about building the solution and existence at the same. We're posing this. This says, suppose you somehow have constructed a solution from some other way, maybe compensated compactness or some weak convergence, something. The solution you get will be stable under L2 perturbations if these two conditions hold. And these are exactly the kind of, these are conditions 1 and 2 in all the old papers, except instead of relative entropy, they always just said entropy. Just eta itself should increase, not this relative entropy. So that's the difference. Oh, it's not. I shouldn't have. I unfortunately, it's a bar. I've been changing back and forth.
Okay, so it's the same definition as there. The definition.
Yeah, it's supposed to be the same definition. Yeah. Okay. And Okay, let's see. And okay, this is a consequence of two lemmas. So the first lemma. Integral from x of t to infinity of eta WR dx. In fact, yeah, this thing that I want to decrease, exactly this thing, is equal to, or sorry, is less, is equal to integral x to infinity of eta sub t minus x prime of t eta of WR. And that is less than or equal to integral from x to infinity of dxq dx, which is equal to negative, is equal to q. Did I write this out properly? No. That's oops. Minus x prime of t eta WR, and that is equal to q minus sigma q of WR minus sigma eta of WR.
What does it mean, Q of W bar there?
Q, okay, so I forgot to define, yeah, and Q here, Q of WR, that's slightly non-trivial. Okay, and I want to make, it has to be an entropy flux. Let's see, let's go. Is Q of W minus Q of WR minus d eta of WR F of W. Sorry, df of W times W minus WR. It's not what you might immediately think. Yeah, I would like to put, it's not the Q of WR. That's what I would like to put there, right, by analogy, but it wouldn't work as an entropy. It still has to be an entropy flux pair to do the job. With, if I hold WR constant, it should be a nice entropy flux. And this is what you need to make that work.
W instead of WR.
Yeah.
That,
Right, it's df of W, not df of W. Okay. And then it's a nice entropy flux. And because it's an entropy flux, we have dt q WWR minus dx, d eta, dt eta minus dx q of WWR is less than or equal to 0. With this definition, I have that, and this is what I'm using here. That's what I'm using precisely here. So that's level 1. I'm actually not, I'm just indicating that proof. I'm not going to go through the details of their proof, but just to show you how it goes. I will give you the details of showing that the condition implies the Lopatinsky. And actually that calculation, though much simpler than theirs, has the same flavor. Okay, so this one is just following your notes. This is just using entropy production. So this is the thing that we need to be, let's see, we need this to be less than or equal to 0. Okay. And that, yeah, okay. Say, yes. Okay, so next step, there's a second lemma. Okay, so this is the magic lemma. The first one was just the setup. And now one computes that Q of W of theta WR minus sigma eta of W of theta WR is equal to the integral from from theta to theta naught. Theta naught is where S of theta naught equals WR. This is a little tricky. Okay. D sigma over D theta times eta of WL W of theta minus eta of WL WR. D theta. And, okay. Yes, and recall D sigma over D theta of D theta is less than or equal to 0. Because sigma is decreasing as we move along the shock speed decreases as we move in the forward direction. So this will be negative when D theta is positive. Okay, so the conclusion will be, so this is a calculation. Yeah, it's a calculation. It's done using, okay, using the ODE for RH and manipulating symbols, and it's very similar to what I'm going to do in a moment, but harder. This one's really complicated, or I would do it. There's many parts. And it's kind of funny. The ordering is kind of strange, right? It's not what you would expect, but this
Sigma is equal to X prime, right?
yes, this is the speed.
So where did we use the assumption that the assumption one?
Oh, assumption 1, that's right here. I'm just mentioning it because now when I prove the main theorem, using okay, so the first lemma says all I have to show is that this is less than or equal to 0. The second lemma says, well, this thing that I want less than or equal to 0 is equal to something else, and it has this factor is less than or equal to 0. This product here. So I need to show that the rest is greater than or equal to 0. So it's just d sigma over d theta. D theta is less than or equal to 0. So condition 2 implies that the the whole integrand is less than or equal to 0. And then we're done. Because condition 2 was that this thing, that's exactly what condition 2 came from looking at this, right? This is what it's not what we need, but it's what we would want in terms of a nice monotone condition that would give us this result. So, and this is actually this is not how they reported it in their paper. The sufficient condition they reported is a stronger condition, and that's the one I'm going to need, which is d over d theta of eta of WL W of theta is less than or equal to 0. And that will ensure that all along this Hugoniot curve, so let's just look. Here's WL, here's WR. We're moving along a Hugoniot curve from WL to WR, and then we're moving back and forth in this vicinity, but we just still want positivity when comparing something here to something here. So it's enough to show that it increases as we move along this curve. So we just need that this be monotone with respect to locally monotone. So instantaneously monotone. We need the derivative of this, be positive. And that will be good enough because we're starting at let's see, I think I wrote this. Yeah, I should have written, let's see. Lemma 1, this one, okay, that's not the one I want. Lemma 2, yeah, theta, okay. Yeah. That's all I want. Right, I'm going to go all the way down to this WL is theta equals 0. So I'm going from theta equals 0 here to theta equals theta naught up here, and I'm somewhere around theta naught, and I just need to know that if I'm somewhere out here, the difference from WL is always negative. But I could be anywhere anywhere theta positive. Anywhere along the shock part of the Hugoniot curve. I can't go negative, that would be a rarefaction. So I'm out here. Okay, so I do get this positivity so long as I have a good derivative sign, and that's the condition 2 prime. And that's the one that they emphasized, even though they actually prove a lot more, but this is the one that this is very hard to, you see, how do you verify this? That's hard. But the other one is easier, just take a derivative. And that has the flavor of those early things, which said usual entropy decreases along the Hugoniot curve. This says, increases. This is very similar. It says relative entropy increases along the curve. We'll replace this appealing condition with another appealing condition, and then we get the result. Okay, so, and that recovers ideal gas to be all the known results, and you can apply it to many systems, presumably, but only to the extreme shocks. But okay, why quibble? This is the only result of this nature that I know. It's and it's very beautiful. Yeah, no. Extreme means that it's in the 1 family or the n family. So, and that was really important in deriving all this because we got to erase one side. Yeah. And in fact, they give some examples, maybe in that paper, maybe in later papers. If you have intermediate shocks, it gets really complicated. It's not so easy to find a contractive norm, and in many cases, it seems you can't. But this one just works very nicely. All right, so
like in the other cases that are counterexample, I mean.
Yeah.
It breaks the arm.
yeah. And also, I should mention that, okay, this is not necessary for stability of shocks. It's sufficient. You could go to a scalar case, scalar conservation law. So to break this, so intermediate shocks for systems, but also non-convex or non-genuinely nonlinear. For scalar. So take dx w plus, sorry, dtw plus dx w cubed over 3 equals 0. So it's say higher order burgers or cubic burgers. We just replace the w squared with w cubed over 3, and you will find, and the yeah, and take for the entropy the obvious one, w squared, sorry, and work this out. You'll find it's not contractive. This condition fails. It fails for, so it's a kind of fun exercise. So w minus equals 1, w plus equals 0. Check for that. Let's see, it's not this condition that this contractivity condition fails. So that's sort of annoying, but that's outside, it's already outside the scope of what people were trying to do, because the physical models with these, I mean, genuine nonlinearity was something that was always assumed. So, but it's not going to do just everything, but it does the nice cases very well. And I had tried many times to do anything with entropy. It seemed so appealing. I never succeeded. I wasted many boxes of paper over periods of a decade, probably. Every summer I would do it, just compute energy estimates and throw it away. Then luckily I'll actually prove something, so no more paper waste. So, okay, but all right, so I'm going to show you. But this really puzzled me. It puzzled me because it's assuming existence, which is sort of tied up in the low potential condition, sort of gives existence and a kind of stability at the same time. This gives a much stronger stability, but it wasn't clear that you get the existence, but it sort of seemed like you should, and you do. And the proof is very much in the spirit of Leger and Vasseur. So this is Texier and me, Proceedings AMS 2015. So a little while after we saw this paper. So we show that 1 and 2 prime imply the low potential condition as well. All right.
The Vasseur paper does not assume this condition.
But they're not. Yeah, they're not. It's actually much stronger than just a low potential condition. It's nonlinear. It's for arbitrary size perturbations, and it's good for L. Let's see, just L infinity solutions, measure valued with certain trace properties, and they get this contraction for the big wide class of data. Whereas this is just kind of a rank condition. It's the start of building a theory that does not allow a super general solution. Like usually has to be very smooth on both sides and different, yeah, much more circumscribed setup, and yet you would want to know this Lopatinsky. Well, it seems like if you get all this other stuff, surely you must get the Lopatinsky condition as well. Or how could this be? That's what we thought. So let's try to verify it. And so here's how you do it. Okay, so first, recall. We have to recall a couple things. So this goes way back, Lax and Gunnoff, or maybe I should write it in the other order. Go back in the 40s, early 50s. Existence of an entropy implies a few things. So it implies that, okay, so entropy eta, d squared eta is positive semi-definite. D squared eta A is symmetric. So we have a kind of a simultaneous symmetrizability going on here. Let's see. And we'll come back to that. Okay, so we have ranking Hugonio looks like this. Sigma S of theta minus WL equals F of S of W of theta minus F of WL. Okay, so now we take the derivative in theta, and we get sigma, oh, this is theta, I'm sorry, sigma prime of theta, S of theta minus S minus WL. It's very much like the derivation of the Lopatinsky condition, right? Instead of dots, we have primes, but anyway, and we get A of S of theta minus sigma of T times S prime of theta. Okay, here I'm using that this one, when I differentiate, this goes away. This has zero derivative, and I'm rearranging of it. This is a fact that we know and we'll use. And then the Lopatinsky condition is determinant of S of theta minus WL R2 of S of, I'm just going to leave out the R2 through Rn of theta does not equal 0. That's the condition we're trying to prove.
When you differentiate, there's no derivative of S.
The derivative of sigma came here, and then, but there was also a derivative of S, and that went over here. That's this one. Yeah, yeah, I did it a little fast, but yeah. Then okay, and then our key lemma, maybe one of the key lemmas, is that 2 prime, which was d over d theta of eta of eta of WL W theta, S of theta is greater than or equal to 0, is equivalent to this condition. S prime of theta d squared eta of S of theta minus UL is bigger than or equal to 0. Interpret. So it's giving us, telling us something relating the derivative of S, the difference of S, and relating in a d squared eta norm. This is like an equivalent inner product, d squared eta inner product. Because remember, d squared eta, this is a positive, definite, symmetric because it's a Hessian. It's positive, definite because of the entropy property. It's assumed to be. Okay, so the proof is, let's see, d by d theta of eta of u s of theta is equal to d by d theta of eta of w, sorry, of w minus eta of s theta minus df of s of theta u minus s of theta, w. Okay, by definition. Just reminding ourselves what it is. Okay, and then that will be, okay. So we have different parts that come out. So let's see, this is when we take a derivative of this, it's going to be 0. This is going to give us some eta prime. This is going to give us some derivative in theta. This is going to give a derivative in theta. No derivative in theta here. Okay, so when we sort things out, we're going to get s prime of theta against d squared eta at s of theta, WL minus s of theta. Inner product. Let's see where it is. So minus d eta of s of theta, s prime of theta. Let's see. No. This is it. Sorry. Okay. I left out a term, it looks like. Starts with negative d eta of s of theta, s prime of theta, minus this. And then this is inside of this. I'm sorry, this is inside of this. And this guy is going to cancel with this. I got a minus, these cancel. So this is gone and this is gone. So let's just see if I can reproduce these. So yeah, so here's when the derivative falls on the s, comes here. When the derivative falls, sorry, here. When it falls on, and then the others are all from here. The derivative can fall on df of ds and on s prime. And where are we getting these pieces? Got a d squared eta coming from the d eta. This is a d eta. That's why there's no f. D eta. That's the definition of, why did I write df? I don't know. That's d eta. That's where the d squared eta comes from. And that goes with this difference. But there's another one where you just have d eta and a derivative on s. That's this one, which actually, but that cancels with the first one. So we get a nice cancellation. We're left only with the middle term. The middle term is what we wrote. So there's not so much to this one. But you have to write it correctly. Okay, lemma 2. No lemma 2. Okay, it's just the proof. Okay, so we've got failure of the Lopatinsky is equivalent to saying that we have S of theta minus U WL is equal to summation of alpha j Rj on the, all these are on the plus side, for 2 less than or equal to j less than or equal to n. Clearly, because these are the things, this is the thing that's supposed to be linearly independent from all these outgoing directions on the right. And let's see. Yeah. And this is by the way non-zero. Let's see. Could it be possible? Yeah, it's not possible. It's not possible that that this not be involved because these are independent. So it must be of this form. Okay, so now I use now I apply A plus minus sigma of theta to S prime of theta, and that is sigma prime of theta summation of alpha j Rj plus. Okay. Plus times why do I have this? I have this because this is the linearized ranking Hugonio right here using this one, star. So it is A minus S. S prime is sigma prime times the difference. Well, that is the left-hand side, so it's sigma prime times all of these guys. That's it. And now I'm going to invert. This is invertible by the lax characteristic condition. And when I invert it, I get S prime of theta is equal to sigma prime of theta, summation of alpha j, from j even or equal to 2 of, alpha j plus rj plus over aj plus minus sigma. And these are all positive. Okay, so let's just call it equals sigma prime of theta summation of beta j Rj plus, and the beta j's have beta j alpha j is positive. That's going to be important. Okay, let's see. So now recall now that P equals d squared eta is positive symmetric. Definite A equals df is symmetric. Let's see. sorry, not symmetric. PA is symmetric. That's the Lax-Godunov fact. So this means A is self-adjoint with respect to the P inner product. So the eigenvectors Rj are P orthogonal. Thus, if I take S prime of theta against P A minus sigma of theta S prime, okay, that is going to be equal to, by our relation here, which I didn't give a name to, but plus plus by plus plus, that is sigma prime, sorry, that is sigma of S squared summation of beta j alpha j rjp rj. Is positive? Okay. These are all positive by positivity of P. But these, remember, these are positive. Which really is by the Lax, that's really just because the Lax characteristic condition means that when we invert by A minus S inverse, we don't change the sign. So these are positive.
Sigma prime is it sigma? The first letter equal in the last.
This is sorry, this one is sigma prime.
Just put it.
Oh wait, let's see. Is it sigma or sigma prime? I think it's sigma prime. Sigma prime. Yeah, sigma prime square. Yeah, and since it's a square, it's positive. I understand. Let's see, why is it squared? S prime against I have a sigma here, sigma prime. Let's see.
Because there are two S prime in a sense. S prime, S prime.
Yeah, that's right. Thank you. Yeah. Yeah, this is still, it's just chasing some symbols and it all works out, but it's a little delicate and surprising. So this is what we would have. Okay, so this would be true. But lemma one says that, recall, it said sigma prime, S prime, P, S minus W L is less than or equal to 0. That was equivalent to 2 prime. The 2 prime condition forces this, it forces the opposite sign. Whereas failure of a Lopatinsky condition implies a positive sign here, and yet the monotonicity of entropy imposes a non-positive sign. Contradiction. And that proves the result. So that is, oh, I went over, sorry. But yeah, so that is, yeah, one of my favorite observations and facts about conservation light. It's the only one that I know that gives such a definitive result for large amplitudes. So I would present that. Okay, so that's the the gym for today. And then next time, I'm going to present the Kawashima theory, Kawashima estimates, which is another real gym. So we're at a high peak here. Okay, so thanks for your attention. Any questions out there? No? Okay. All right. Yeah, we will. You on Tuesday. Right.
Thank you.
That's the hard part, But which?
Right quantity too.